dear authors and invited guests. Welcome to Technical Session 2D. On behalf of Global Knowledge Research Foundation, it is my great pleasure to welcome to the 7th International Congress on Information and Communication Technology through Zoom. Further, as you are all aware, we have been facing new normal situations while overcoming the pandemic. Hence, the conference has been shifted to a hybrid mode. We are very thankful to everyone present on this platform to go along with us digitally for the conference in these unpredictable times and making this conference more productive. Also, there is a note for the presenters. You will be given 10 to 12 minutes for the presentation and 3 minutes for question and answers. So on 10 minutes, I will raise a reminder. And I also request the other presenters to be on mute while the presentation is going on. Also, before we start, I would like to introduce our session chair, Mahesh Bundel. Just a minute. Dr. Mahesh Bundel has completed his bachelor's in electronics and power in 1986 from Nagpur University and immediately joined as a lecturer in electronics at Baba Saheb Naik College of Engineering. While working, he has handled various portfolios related to design and development of design and execution of laboratories, etc. He has guided many research projects at UG and PG level on various applications in electronics and computer sciences. I welcome you, sir. So we have our first presenter with us. Bolsit Yon, are you here?
Yes, I'm here.
So just a minute. So you are presenting on just a minute. Convolutional neural network combined with active contour for image RGB segmentation, right?
Yeah.
Thank you so much. You can start with the presentation.
You see the screen?
Yes, I can see your screen and audible as
okay.
well.
Good. So good afternoon, everyone. My name is Yoann Boussy. I'm a PhD student at the Hubert Curien Laboratory in Saint-Étienne in France, in collaboration with the company Singular Technology. I'm here to present the result of one of my works, which is the association of CNN, convolutional neural networks, with active contours on RGBD images. Image segmentation is a long-standing problem as it affects many applications. Several approaches have been proposed to address this problem, including segmentation CNN and active contour. CNN has good results and outperform other approaches in complex images and complex contexts. Active contours, a deformable model approach, consists of deforming an initial curve using forces until this curve can no longer move, particularly when the forces cancel out or are equal to 0. The solution proposed in the literature combine the two methods, CNN and active contour, to finally segment objects on RGB images as they allow a better understanding of the image. The CNN will be used to segment the image and predict the contour of the object, while the active contour will refine this contour toward the ground truth contour. These solutions combine a method that take into account high-level data, CNN, with a method that take into account low-level data, active contour. The solution proposed in the literature use active contour in post-processing, mainly in the medical field, such as cell, tumor, or heart ventricle segmentation. They all use the level set method. This method is based on the theory of curve evolution. It iteratively moves a front that is a set of points that have the same function value. It is a non-parametric model, so it doesn't require any parameters. This method allows the segmentation of several objects with the same property, like a strong contour clear object, with a single initial contour. It handles change in image topology automatically. The biggest drawback is the complexity of finding an initial function that resembles to the initial contour curve. In the literature, there are no articles that consider RGBD images in active contours. RGBD images, RGB for color, D for depth, deal with live scenes with complex objects that is not having their depth and or color of the same intensity. This is one of the reasons why the level set method is not well suited to our problem. So the first part will be devoted to the CNN plus active control method, and in particular to the forces put in place. The second part will present the results obtained with its method. Finally, I will conclude with perspectives on the proposed method. So now I will describe the proposed method. The overall process described in the figure consists of 3 parts. The first part is the choice of the CNN. Okay, here. The second part is the initialization of the curve and selection of forces. And the last part is the application of these forces on the active contour. The first step, which is the selection of the CNN, is a step that is adapted to the context and the database used. The CNN processes the image information at a high level. This processing has the advantage of obtaining information close to human reasoning and detecting classes of objects. In our context, the RGBD CNN with the best accuracy is the GAD with 59.6 IOU on the NYUV2 dataset. The higher the accuracy of the CNN used for segmentation, the more accurate the initialization of the active contour is, which avoids error when applying the active contour. The second step is the initialization of the active contour with the labeled images from the CNN. This is an important step that sets up the rest of the process. This includes the initialization of the image that allows the calculation of the forces and the initialization of the curve of the object. The forces and the initial curve are the inputs to the active contour. The forces used to update the active contour are internal forces, forces that take into account only the position of the point of the core of the contour, and external forces that take into account information from the images in the scene. The forces we are most interested in and which have a great impact on the final result are the external forces. The type of forces selected are the gradients and JVF. Gradients are used to detect contour, and gradient vector field is equivalent to the magnetic field of this gradient. In order to be able to take into account the complex characteristics of the object, the forces will be exerted on the RGB image, the depth image, and RGBD image, which is a multiplication of the previous images. The initialization of the curve is as important a step as the forces. The CNN doesn't deliver a curve, but a set of points with the same labels representing an object. Furthermore, the final segmentation doesn't take into account neighboring pixels, so that they are pixels inside the object that are not of the same label and that can alter the initialization. An opening that is a deletion followed by an erosion removes this erroneous pixel. The extraction of the object contour is then carried out. To limit the number of points to be processed, 10% of the control points are kept. They are selected so that they are equidistant from their nearest neighbor. This equidistance is important because it allows the final object to be segmented and its entirety and prevents the active contour from under-segmenting center part of the final object. The last step consists in deforming the active contour thanks to the contour and the forces initialized previously. To do this, it is necessary to calculate the sum of the energies and the different forces, which will then allow the selection of the neighboring pixel with the highest energy. The gradient energy are normalized with respect to the maximum gradient of the treated area. The GVF energy is calculated differently due to the nature of this force. The GVF is a vector. The energy is calculated by taking the vector product of this vector and the neighbor and the center neighbor vector. The result is normalized by the maximum of the treated area. So here you can see the GVF energy and here gradient energy. And here you can see the sum of the two energy. So an example on the right shows how the energy and the two forces are calculated. The two types of forces are also to be calculated for the associated depths and RGBD images. It is a set of internal and external energies that will determine the next position of the control point. At regular intervals, the points of the curve are rearranged to be equidistant to correct the dispersion of the points. So now I will present you the result of the test. In order to verify that the proposed method works and how accurate it is, tests were carried out on the NYU V2 database, a labeled RGBD CN database. A test was performed on 115 objects, about 13 classes. All combination of forces were tested. The 11 forces were set as present, value equal to 1, or not, 0. At the end, the total and class accuracy was calculated and the best force combination was found. The results shown in the table opposite highlights the fact that the external forces have a great importance in the quality of the segmentation, in contrast to the internal forces. The gradient of the three image types are present in the top one, as well as the GVS forces and the RGB and depth images. The method allows an improvement of the segmentation in 62% of the case by 8.3 IU on average, with a maximum gain of 16.7 and a minimum of 6.4 IU. These results show a significant improvement in the final segmentation. As you can see, the image are the results of the method. The layer curves are the ground truth. The blue curve is the initial curve of the active contour, and the pink curve is the final curve after the active contour. We can see the segmentation of the object with our method is near the ground truth contour. So now I will give you my conclusion and the perspective of the proposed method. In conclusion, the proposed method improved the segmentation thanks to the cessation of segmentation CNN and active contour in RGBD images, although some categories of objects like classes and table don't respond ideally to this method. It should be noted that the strengths have not been refined. The refinement of the strengths by class, thanks to regression, for example, is an interesting prospect, which would make it possible to improve the method even further. In addition, the fusion of different objects in the scene should be explored. This fusion would make it possible to avoid pixels with 0 or 2 labels. These application domains could be multiple, such as industry, robotic, or medical, because they use high precision image segmentation. So you will find in this slide the reference quoted throughout this presentation. Thank you for your attention.
Yes, any question from the audience, participants? Yes, you have used different methods and two different data sets, I suppose. Is that
yes,
it?
so, I use NYU2
yeah.
data set with a huge data set and is only label. I can.
But you taken only 115 examples.
Yes, because the computation is very the time to the computation is very long. So I want to prove the methods work.
But the accuracy you are getting 54, maximum 54, 55.
Okay. I analyze 115 examples in
Yes.
this data set.
Yeah. So you are getting 54 point something or 55% accuracy.
Yes.
Why so? What could be the result?
54. Okay. Okay. Can you repeat?
Yeah,
the question?
you are the accuracy you are getting 54, 55. Accuracy, you go back.
54.
Yeah, back. Yes, no. Again, previous slide. Yeah, here 59.6. Maximum accuracy you are getting is 59.6. Previous one.
Yes. Okay. So the GAD. Okay. 59.6. It's here. It's GAD. So I use this CNN because it's the best in this data set for RGBD images.
But then 59.6 accuracy is very less.
Yes.
And you said that it is high precision. It can be used in high precision applications.
It is the best. So
it is based amongst the methods and the variables you used.
Yes,
but it is not 100%.
It is the best in CNN, but not with my methods. My methods improve the result of the GAD.
How it can be improved further?
How I can improve because the CNN obtain I can obtain labeled image after the CNN, but the CNN don't have the low information of the image, and the active contour is a method just
you use force values 0 and 1 only. Can you have some intermediate values further? Forces whether you have taken 0 or 1. Forces I am talking about. Forces.
I don't know what you
want,
but the CNN after CNN I have a labeled image, and it's high information, and with active contour I can have the only the low information, and like that I can improve the output.
Thank you. Yeah.
Thank you so much for your presentation. So we have our next presenter, Milan. You will be presenting on fault tolerant distributed mutual exclusion over elastic logical ring topology. Thank you for your presentation. You can start with your presentation.
Thank you. Could you see it, please?
Yes, I can.
Thank you. Dear colleagues, thank you for the possibility to share with you some part of my work. Under mutual exclusion is understood preventing of any opportunity more than one active object to access a shared resource at a time. The main pros of the distributed ring-based or token ring mutual exclusion algorithm its simplicity. But the main drawback of this attractive algorithm in its basic definition is the strong presumption of absolute system reliability. That's the reason to formulate our objective through suitable modification to overcome the main shortcoming of the basic algorithm, the inadmissibility of process failures. Free working recovery schemes are considered through the overall project class of fault-tolerant distributed algorithms for mutual exclusion over elastic logical ring topology. Under scheme 1, it's assumed that no changes in the system configuration are made. This modified distributed ring-based mutual exclusion algorithm, MX1ME, allows distributed system recovery from multiple faults. It's already published. With scheme 2, the system recovery begins as soon as a process failure is detected. This is at the expense of excluding the faulty process from the system configuration. That leads to ring shrinking or one-way resiliency and represents a kind of graceful degradation. This work is also already published. Here is described scheme 2, which supposes both exclusion of the faulty processes and inclusion or injection of faultless pair processes. So combining both scheme 2 and scheme 3, which evolved from scheme 1, the communication ring acquires the property of two-way resiliency. All three recovery schemes share almost the same chain of helper distributed algorithms. Output channel error handling algorithm, communication ring checkup, distributed ring-based election, and token management and recovery algorithm. At the end of this chain is placed the modified distributed ring-based mutual exclusion algorithm. What is new in scheme 3 is the addition of the helper distributed algorithm I and J for process injection into the communication ring. Under injection, implemented by the ING helper distributed algorithm, we understand such a change of the system configuration, suggesting addition of new process in it. At this table, we could fold a normal, it is without any faults, execution startup sequence. Here is the graphical representation of this sample. Let's look at the segment of the system ring. The segment contains three processes, Pi minus 1, Pi, and Pi plus 1. The process Pi is currently excluded from the ring because of its failure. The ING algorithm consists of three phases: opening, forwarding, and closing. At the opening phase, the injected process, here it's noted as Pj, initiates the operation sending to Pi plus 1 the message injection Jk. The first item, mark injection, is the type of the message. The second parameter J is the identifier of the process injected, and last, the third parameter is the identifier of the process immediately in front of which Pj is to be placed. In our case, K equals to I plus 1. At the forwarding phase, the injection message, injection JK, is forwarded by each process until it reaches the process PJ. Furthermore, the identifier J of the injected process is inserted into the list of system process identifiers, list PITs. At closing phase, PJ receives its own injection message from PI minus 1. As a side effect, this event corresponds to one ring up event of the communication ring checkup algorithm. Next follows the formal specification of injection algorithm. It begins with synopsis, assumptions. The declarative part contains the system constants needed, messages exchanged, set of states, and internal states space. The third part of the algorithm defines event handlers. Here we called several events on initialization, on output channel connect, on injection start, on receipt of injection message, and on timer. The key event is, of course, on receipt of injection message. Firstly, is check if identifier I, the identifier of process PI itself, equals to the identifier of injected process. If so, we go into the closing phase. Otherwise, we go into the intermediate forwarding phase. Here, the next diagram, we can see the general event diagram representation, which consists from the sequence of occurrence of system events caused by the system. Let's focus us on a simple example of stretching. Let's focus our attention on a possible scenario, which suppose we have a system from 3 processes, but initially only the process P1 is available and unfolded. Initially, the least speeds of this process includes all 3 identifiers. But after the execution of the whole change of algorithms, the system will reduce to its smallest possible dimension as shown here. In this case, the election algorithm will select P1 as a coordinator, which is marked in a red circle. At next phase, phase 2, let's try to inject the process P3 by sending the injection message from it to P1, the appropriate injection message. When the procedure is over, we will have a ring from 2 processes as shown and the respective list of process identifiers in both of the unfolded processes here. Note that in this case, the injected process P3 doesn't not know yet that P2 is faulty, but this is not required, as every process in the ring is only responsible for its output connection. Here, the P3 is selected by election algorithm as coordinator. At last, at phase 3, we try to inject the second process, the P2, by sending from it to P3 the injection message, injection to 3. When it's over, we will have a full ring from these 2 processes. Here, at this table, we could follow the execution trace of a run of the above presented scenarios, phase 3. These tables are with using the received using the algorithm test bed developed and published in GitHub. As conclusion, we could say next, the subject of the article is the third of the free recovery scheme developed. The scheme 3 fail recovery with two-way resilient configuration, which involves from the previous two. Here is shown the modification of the chain of algorithms for resiliency and the generalized formal specification of the injection operation. As a result, we get elastic ring-based logical communication topology. It shrinks at process failures and stretches at process recovery by its injection to the current ring configuration. The algorithm testbed is implemented with the Embarcadero C++ builder development environment and its Clang enhanced C++ compiler. The testbed itself, as the evolution of the testbed, can be traced on the appropriate GitHub repository. Here is the list of references. Thank you very much for your attention. Thank you very much.
Yes, any question from the participants? So you have not done any kind of simulation or testing
yes.
of, yeah, you're just given some example. Did you carry
Yes.
out some simulation using these algorithms?
Yes, with the testbed developed, we have simulation, but you can see that this is simulation, but in fact, this is example how to realize the algorithm itself.
Okay.
Because the models from which the simulator consists are ready models for embedding in a real system.
Okay. Okay, thank you.
Thank you. Thank you for the possibility to share it with you.
Thank you. Thank you so much, Milan. Thank you. So we have our next presenter, Harry. You would be presenting on second order adaptive network model for collective emotional response during reward-based gaming. Right?
Yes, thank you. Yes, together with Joy.
Thank you.
Thank you.
You can share your
I
screen.
will share my screen. All right. Thank you all. So, welcome to our presentation about collective emotional response during frequent repetitive reward-based gaming. Today, we're going to present you our second order organizational learning model for emotion-based skill building in joint gaming. And this is presented to you by me, Harry, and also Joy. And Jan is also in the meeting, by the way. So we will present you our background first, so why we chose frequent repetitive reward-based gaming. Then I'll explain about organizational learning. I will explain about our model, so the design, the simulations, and also the additional exploration that we did. And we will finish with a discussion. So first, we chose for frequent reward-based gaming because the amount of multiplayer gamers has increased, and the expectation is that in 2023, almost 3 billion people around the globe will be playing multiplayer games, meaning that that would be almost a quarter of the global population. And for this project, we use the term frequent repetitive reward-based gaming. And that is basically online gaming in which you get rewards based on achievements. And working together makes getting achievements easier. So what that means is actually that multiple actors play a game and they need to conquer flags, for example. And this would be then their goal. And this is possible through teamwork in a squad. And that squad is basically a group of people together that communicate with each other, but also learn from each other by listening to what the others communicate. So we use organizational learning for that. And in the context of this project, it means that the squad can receive information from the actors, but also that the actors can receive information from the squad. So basically, the squad is its own entity, is another entity. So for our model, we make use of two actors, two independent actors, and then the shared model. That's a separate entity that gets information, but also relays information. And a logical question to ask is then, why use organizational learning if you learn from each other directly? Well, the thing is, in modern multiplayer games, the squad can also earn points, and these points come in through teamwork player activity. And that's the player to shared part, but also there's a shared to player part, because being a good squad leads to privileges that aid in reaching the achievement in a game. So for example, in some games, because of those points, you can call in support, which helps you reach your achievements faster. So moving on to the design, we just quickly wanted to give you an overview of the functions we use. We used a lot of mathematical functions, which are sometimes complex. We're not going to explain everything about this due to time constrictions, but just know that we made use of a lot of dynamics. And we want to show you our base model. And our base model starts with encounter. So we assume that the game has already started, and now the players are walking within the game environment, and then they encounter an opponent or a flag or something. Then they start building up their concentration because the gamers realize the encounter and focus on the game even more, tapping into their skills. And this increase in concentration means they are being able to access and enhance their learned skills. And they use these skills to gain achievements. And these achievements increase as skill increases. So when actors become better, the results of playing are improved. And this is when we get to the emotional response and feedback part. So when they get an achievement, you can get positive feedback, which is happiness. And this happiness gives feedback to the concentration loop. And this is positive feedback. So basically what happens is when you have happiness, the concentration increases, and that automatically makes the skill increase and the achievement increase. But lack of achievement will lead to an increase in frustration. And this frustration has negative feedback on concentration. So if there's frustration, there's going to be less concentration, less skill, and less achievement. So there's an interplay between each other. And now we want to show you the layers of our model. And from this slide, you only need to know that all three actors have the same base model, but they are not connected to each other in the base model because it's a top-down model, and that I will explain in 2 slides. What you do need to know is that most of the connections are adaptive, and that means that the weights are modifiable, regulated, self-regulated, except for frustration, and that is because there was no scientific consensus on the use of negative adaptive learning. So we chose to make that a direct negative connection. Now I'm going to show you our top-down learning system that we use. So for organizational learning to be implemented, we implemented feed-forward learning and feedback learning. And feed-forward learning is about communication. So it is about the 2 actors giving information to the shared model. So if you increase communication, they are better at giving communication to the shared model. And then feedback learning is about the shared model's information being interpreted correctly by the actors in return. So that's the listening part. And if you improve that, then they are good at listening. And as you can see, our model is quite complex. That you can see that in the picture, the image down below. But now we're going to take you through the simulations. We made use of 3 different simulations, which are good communication and good listening. This means that you are familiar with the game, but also familiar with each other. So that means that you already know the game, so you know the objects in it. So you're already used to saying that the enemy, for example, is at the yellow barn instead of saying the enemy is at that building, which is rather vague. And you're also familiar with each other because you know each other, you know what language each other speaks, and you know how to address them. Then you have bad communication and good listening. So then you are unfamiliar with the game, but familiar with each other. So you know each other, but now you don't really know the game. So you're just going to say, okay, the enemy is at the big building, which is more vague than the enemy is at the yellow barn. So you're starting to play a new game together. And then you have bad listening and good communication. This means that you're familiar with the game, but unfamiliar with each other. And you could interpret this as a language barrier scenario. For example, that one person speaks Dutch and the other person speaks English. And in that case, the yellow bar, yellow could mean something very different in Dutch than in English. And now I'm going to give the word to Joy, who will explain our results.
So in this first graph, it displays a good communication and good listening. You can see initially that both the concentration and the skill of the actors rise, as well as the frustration. However, as time passes, you can also see the yellow line that the achievements start to increase. Due to this, that both actors become happier, in which the frustration inhibits and becomes lower. Then in the scenario of bad listening and good communication, you can see that the graph is almost the same, except for one thing. At the bottom, you can see that one of the actors has a lower concentration as well as lower achievements, leading to underperformance of one of the two actors. This due to, although good communication is present, the listening of one of the actors is bad. Therefore, the skill of the second actor doesn't get improved. Then in the last scenario, in the bad communication and good listening, you can see that the graph is entirely different. Not only does the blue line fluctuate, you can see that the happiness of the actors has flatlined. This due to communication being bad, and that communication being the first step of good teamwork.
Okay, and we performed the evaluation. We tried to explore more in the model. And for that, we really wanted to look at emotion regulation because that's what our model initially was about. So we divided happiness by frustration and we created an HF ratio, happiness frustration ratio. And what we saw was actually a clean S-curve, and we saw this for most of the graphs, but then we looked at the bad communication graph and we still saw somewhat similar dynamics, but very low Y values, as you can see. So the proportion is really small, which led to our hypothesis, which is that we wanted to recreate the dynamics of the optimal communication and listening situation. So the HF ratios being an S-curve, but then in the case of bad communication. So tuning was performed to explore other situations with same dynamics. And we used the ratio between happiness and frustration as a basis for that. And what tuning basically does is you can input the ranges or the dots on the graph that it needs to go through, but then the tuning parameter, the tuning chooses random variable amounts to get to that dynamic. So it tries to find different situations in which this dynamic is true. And we actually found one of those situations, and it showed that our model is rather flexible, meaning that you could change some variables and still get the same results. So there's a lot of possibilities with this model. That's what we realized. And we also verified it using a comparison to our old dynamics. And we saw that the line was very close to our original lines. Moving on to the discussion.
So we conclude that a successful model was created for FRBG that makes use of organizational learning and simulates emotion response in relation to skill building. However, there are a few limits to the model. For example, emotions always have the same effects, and we only use 2 emotions. However, in reality, people have more than 2 emotions. We also made use of static context factors and the static encounter rates. However, anyone that plays games knows that encounter rates aren't always static. As for recommendations for future use of the model, we want to clarify more empirical validation, as well as the addition of new nodes, which include more emotions, context, and more actors, to really signify the group dynamic of the entirety. Lastly, we want to think of outside of the box solutions, including communication and listening adaptation, also including differences in encounter rates.
And with that, we would like to thank you all for your time and for listening to our presentation and ask whether you have any questions.
Yes. Any question from the participants? Audience, please. So what kind of data set whether you created your own data or You use some standard data sets.
We made use of our own data, but we tried to compare it to how the dynamics would evolve within the gaming community. So we really compared it to situations that we ourselves recognize during gaming. An example could be
So how
gaming.
did you ensure the emotions while collecting data?
Sorry, could you repeat the question?
You use two emotions.
Yes.
Yes.
So
Happiness and
how did
frustration.
you ensure that the emotion is true emotion?
How did we assure
Yeah.
that the true
Yeah,
emotion?
emotion
Okay.
is true, whatever you are recording.
Well, at the moment, that's exactly what we say in our recommendation as well. We do not have empirical validation for that yet, so we really do need that to verify and validate the model. At the moment, we have mathematical validation of the model, so we know the model is working correctly, but the connection between the model, so the simulation, and the real world is still something that needs to be explored.
Further, you said it is adaptable or modifiable. How is that?
I'm sorry, what? Could you repeat?
Adaptable, somewhere you used adaptable or modifiable.
Ah,
model.
the adaptive, you mean that the model is adaptive,
Yeah,
right?
yeah.
Yes. What we mean by that is that we enabled the adaptivity of certain weights. So for example, some people might build up skill faster when they are experiencing an increase in concentration, whereas others do not have that. And you can condition this variable. So for example, over time, it could be that you are getting better at converting that concentration into skill. So that's what we modeled into it.
Okay, okay. Thank you.
No problem. Thank you for the question.
Thank you so much. Thank you so much.
Thank
So
you.
we have our next presenter, Roman. You are here. You will be presenting on comparison of modern methods of classification of EEG patterns for neurointerface systems. Yeah. Welcome. Thank you so much. You can start.
Hear me?
Yes, I can hear you. You can start sharing your screen.
Okay, I try to share my screen. And you can see my presentation.
Yes, I can.
Good. My name is Roman Buti, and I'm a second year postgraduate student, and I'm studied in Institute of Telecommunication and Global Information Space. And the topic of my paper is operation of modern methods of classification of EEG patterns of neurointerface systems. What is the article about? The architecture provides a research of efficiency of popular classifiers for problems of analysis and classification of EEG signals in brain. From a point of view of classification accuracy under the same conditions, the following classification are compiled linear classifiers. It's a linear distribution analysis, adaptive LTA, and vector-based and matrix-based LTA, and etc. Despite the significant variety of existing classifiers and different approaches to the organization of research using the interface systems, there are few publications where an experiments evaluate of the effectiveness of different methods of EEG classification under the same conditions of, e.g., registration in the interface systems. Given the above, the aim of this article is to eliminate the shortcoming. Namely, this paper solved the problem of experimental evaluation and comparison of effectivity, accuracy of modern classification methods which are widely used in neural interface systems. In order to conduct our research, we have developed our own neural interface system in the develop it based on results of the work. It is proposed to identify 5 main stages for signal processing. It's a signal collection stage, signal preprocessing stage, evolution of signal characteristics stage, classification stage, and finally a computer interaction stage. Here are functional and non-functional requirements that we can set for our future interface system. The interface system must be efficiently proposed. Electroencephalograph signals are recognized to the control action of the human operator, which increases the accuracy reliability. The interface system must serve as a platform for experimental research and search of new effective methods, mathematical models of the classification of the electroencephalograph signals. The electroencephalograph to be used in the interface system must be available for proposed or easy to make with your own hands. And the number of channels in the EG should not be less than 8. And the EG power supply must have a low noise level, reduce errors during the experimental measurements. Power can be supplied from the standalone source, as batteries, accumulators, etc. Data exchanging between the EG and the computer should be wireless. And finally, the software should have a intuitive graphical interface, and the software must be allowed to modify the algorithm for processing the received data. And next, in the article, comprehensive analysis of the interface technologies of the problems of the reasonable choice in human-machine information systems, the authors analyzed the market of available inexpensive interfaces. From this, we can conclude the best solution for the role of the signal registration model can be chosen open source brain computer interface platform, OpenBCI in short. It is a cheap and programmable open source platform. In this diagram, we can see the architecture of the hardware part of the interface system. The main core of the platform is analog to digital converter called ADC 1299. This is analog to digital converter is a low noise, has 8 analog channels, and has a resolution of 24 bits. And using the documentation from the official OpenBCI sites, we designed the open PCBs and made the hardware of the platform or yourself at home. And so all the necessary components were also printed in 3D printer. And It's OpenBCI GUI. It can be used for the to just EEG and primary research. We also tried to create open software to work with OpenBCI hardware platform. Here we can see its architecture, and the methods of non-invasive electroencephalography was chosen to requisition the electricity activity to the scalp of surface. Signals were recorded using the 16-channel version of OpenBCI platform. To fix the electrodes, we used the Ultra-Cortex Mark IV headset. It was printed in home 3D printer. To implement the classifiers and the process of the obtained results, we use our own scripts, write it in Python using the following libraries. It's NumPy, SciPy, Pandas, etc. And finally, to obtain reliable results of the experimental four-fold cross-check on the training data was used at these criteria of selection of selecting the parameters of the classifiers was taken as the average accuracy of the classification. The obtained results of the accuracy of classification of the considered classifiers are given of these two tables. When we recording the EEG, research participant had to perform a number of tasks. The duration of each task was 20 seconds, performing two different actions of 10 seconds each for task for chosen for the experiment. So in the first task, research participant had to bend and unbend the thumb and then the index finger. In the second task, research participant was allowed to smell perfume and ammonia. In the third task, research participant watched a sad and funny video.
Dear presenter, you have 2 minutes left.
Yes, in the last task, research participant listening the light and hard music. And the results of the experiment indicate the linear classifiers provide a good classification accuracy. Due to the simplicity and reliability, they are a good choice for solving the classification task of EEG signals in the interface system. Also interesting is the result which that the linear classifiers as matrix and vector LDA have greater computational complexity that the simple LDA, and they can be useful in a case where the global data structure is not consistent with the local data structure or the input data class or not Gaussian distribution. And finally, then PNA classifiers has also shown a good results in some cases. It can be useful in the task of classification, e.g. a signal provided that the training sample small in the training sample is small. And in this article, an experimental research and accuracy compared of modern methods of classification have been conducted sustaining equal conditions, the same technical condition of recording EEG signals, the same set of input data of classifiers, and same methods for pre-processing and the same methods for evolution the characteristic. And that are widely used in modern interface systems. And thank you for your attention.
Yes. Any question from participants? You have considered 4 tasks, isn't it?
Yes.
So how did you means how the data was collected? What was the size of it? How many samples?
Every task collected at 20 seconds. And
20 samples for each task.
Yes.
So did you consider with the normal standstill position or without any task that data also?
I cannot hear you clearly.
Okay, what was the architecture of MLP used?
We used in the first for collecting signals, we used OpenBCI platform, and in the next stage we used a common average reference method, and for remove any artifacts we use fast Fourier transformation.
Okay, thank you.
Thank you.
Thank you.
We have our next presenter, Shana, who will be presenting on transfer learning approach for railway technical map component identification. So are you here?
Yes.
You can start sharing your screen.
Can you see
Yes,
my screen?
I can see. Yes, yes.
Okay, thank you. So, good evening, everyone. I'm Rochan Ramalshan from Sri Lanka. In our research project, we have used transfer learning approach for railway technical map component identification. So, this will be the content that I'm going to cover in this presentation. So, moving with the introduction first. So before moving on to the problem statement here, I would like to give you an idea about these railway technical maps. Basically, a railway technical map is a complex diagram which includes all the components that are related to railway tracks. So if you consider this figure here, this is a actual railway track, railway technical map. So in these horizontal lines, the railway tracks are depicted, and other symbols correspond to the railway technical map components. So for an example, there are signals, there are switches, there are milepost markers, there are clearance points, and many more. So in our research study, what we were interested in was this relationship between each and every component and their corresponding milepost marker. So here, if you consider this figure as an example, what this actually means is this 5-way switch is located in the actual railway track where this milepost marker 26.0235 is located. So that's the idea. So moving on to the research problem here, two reputed companies from the railway industry are having more than 60,000 PDF pages of these railway technical maps, and these are only available in the form of portable document format files. So a digitized database that includes all the component data and their respective locations is lacking. So having such digitized database will improve the decision-making processes, and it will also assure the safe travel for passengers, and also it will help in many ways for railway maintenances as well. And considering the objectives, our main objective was to define an automated system to identify and read this map component data and to create a formatted text file per a given image. And due to this scarcity of the training images, we try our another objective was to identify these map components using a minimum number of training images. And the third objective was to identify the best object detection model out of single shot multi-box detector, YOLO version 3 and fast RCNN models for these type of digital railway technical map related problems. So if I am to give you a brief idea on this complete system input was and output, actually what we were trying to do is define this fully automated process to come up with this kind of output CSV file when you are given with this kind of railway technical map as the input image. So as you can see here, this kind of relationship is mapped into a single row in our output CSV file. So moving on, moving with this background and literature, as you all aware, there are various state-of-the-art object detection models available. Out of them, single shot multi-box detector, YOLO version 3, 4, 5, and mask RCN and fast RCN are at the top of that list. Also, when considering the optical character recognition, Google provides an enhanced OCR engine called Tesseract. And when considering the related work, still a fully automated work for digitization of these railway technical maps is lacking. But there are some engineering drawing digitization tasks done before this, and there are some license plate identification which uses OCR. And moving to the methodology. So because of this received data was higher in resolution, we had to reduce the resolution of these images first. And after pre-processing this data set, we have chosen 8 labels for our dataset annotation task. And we have chosen these 8 labels. And we have used this label IMG tool, which is available on GitHub, which is an open source tool for our dataset annotation task. And considering the complete system architecture here, this is what I have been discussing in the previous slide. So after this initial phase, we have trained several object detection models using this YOLO version 3 object detection model implementation to identify an appropriate hyperparameters for this particular task. And we, after identifying this somewhat appropriate hyperparameters, we have used them to train another two object detection models using SSD and fast RCNN architecture. So after training these models, we have exported them and we have tested and validated them with our test data set. So after identifying the best model which has the highest performance measures, we have used that model to identify the regions of interest. And after that, only these identified regions of interest are being sent to this post-processing and optical character recognition process. Before sending them to the OCR process, we had to do some pre-processing. I will talk about that in the next slide. So even after OCR process, there were some unwanted characters, so we had to use some character filtering methods for to avoid that. And after that, we was able to come up with this final output CSV file for a given image. And as I said earlier, this is the reason for needing a pre-processing technique before moving on to the OCR process. So as you can see here, these identified regions contain some unwanted portions which are not needed for the character recognition, optical character recognition process. So as you can see in this figure, these switch symbol portion and the track part is not needed, and it is somewhat distortion for this optical character recognition. What we need is only this 9 character. So we had to use some seeded region growing techniques and masking techniques to remove these unwanted regions and come up with this final character only region. Also, when associating these components with their corresponding mileposts, we have identified 3 issues. The first one is these X1 and X2 being not identical. And the second problem was some of these identified regions contain more than 1 milepost markers. And the third problem was more than 1 component being belong to the same milepost marker. So to resolve these 3 issues, we have come up with an algorithm to associate these mileposts with the corresponding component. Actually, we have declared a tolerance level, and we have given each and every component a chance to compare with each and every milepost. So that's the approach we have taken for the, to associate these mileposts with the corresponding to associate these components with corresponding milepost marker. And when it comes moving to the results and discussion, these are the loss graphs obtained from TensorBoard model performance monitoring tool, and these are the hyperparameters that we have used. And as you can see, the mean average precision value is somewhat lower, and these are the results obtained for a single shot multi-box detector. Still, it is these mean average precision value is lower than the YOLO version 3.1 actually. So in this fast RCNN model, we have used the same hyperparameters, and we have able to come up with some promising mean average precision value for this used data set. And considering the result summary for object detection, the fast RCNN model had the lowest total loss, and also it had the, as you can see in this graph here, fast RCNN model had the highest performance measures, all for these mean average precision, mean average recall, and the mean average F1 score. So as I said earlier, when we are not doing this pre-processing before moving to the optical character recognition process, there were some unwanted characters detected. Even though we have used some pre-processing techniques before moving on to the OCR process, there were some unwanted or additional characters. So we had to use some character filtering methods. After that, we were able to come up with the result that we were expected at first. So moving to the conclusions, actually we were able to complete this task or train our model using a fewer number of samples. Actually, we only had to use 69 data set, 69 images of data set, and it is proven from the results that before moving on to the OCR process, it is required to do some pre-processing. Also, fast RCNN had the highest MAP value for these kind of railway technical map related applications. And as I said, as I said earlier, uh, uh, this database is very useful for railway transportation management industry, and actually we were able to come up with this fully automated framework where it requires only the image directory and which outputs the CSV file image set. So these are the future work. So actually there were totally there were 15 components. We have only considered 8 components. So that is a future work, and also the uh, component associative algorithm is not the optimal one, so we have to work on that as well. And as I said earlier, these before moving on to the OCR process, there needed some pre-processing techniques. So what we have done is only applicable for these switches and signals. So each and every different component needed some different pre-processing techniques. So that is a future work as well. So these are the references that I have used, and thank you.
Okay, anybody, any question? So it's a good work, very comprehensive seems to me, and you considered PDF images.
Yes, the data set was originally from a PDF files. So first we had to convert them into images, then we worked on those.
And yes, collected only 69 images out of that.
Actually, sir, due to this confidentiality of these images, we were given only 17.
Okay. Some partial data was given to you.
That was the reason, sir. Yes.
Okay. So how do you think that the actually it can be used for digitization of previous records, whatever application you are targeting?
Yes.
So, but how can you achieve further precision in your or your faster RCNN has given you better results?
Yes.
But it has to be 100% correct, or rather near 100%. So
yes,
how
actually having some more images would increase this performance measures, because for an example, there were only 2 or 3 electric switches in this complete data set that were given to us. So having some more images,
data,
yes, it's
can improve the performance of that.
Yep. Yes.
Okay, thank you.
Thank you, sir.
Hello? Hello, can I share my screen?
Yes. No, screen is not visible. You are visible.
Is it okay now?
No.
Is the screen visible?
No, no.
How about now?
Now, yeah, now it is. Yes.
Okay. Okay. So good day, everyone, from ICICT 2022 London. I'm here to present the paper ID 439 entitled Filipino Sign Language Recognition Using Long Short-Term Memory and Residual Network Architecture. I am Myron Darren Mustalcon from National University, Manila, Philippines. So here are my co-authors, Gerald Padilla and Mr. Roman Rodriguez. So first, I'll be talking about the problem, followed by the known sign language recognition approaches, and our approach, the results and key findings of our study, and finally, I'll talk about the conclusion and future direction of our study. Now, more than ever, it is clear that communication is an essential part of our life. Through communication, we are able to connect with others, share our experiences, thoughts, and wants. And communication is a vital part of our society. However, there are certain groups of people, the deaf community in particular, who are incapable of the conventional way of communication. And for them, communication is their number one struggle. So in the Philippines alone, 1.23% of the total population is either deaf, mute, or has hearing impairment, and this is more than 1 million individuals. So the deaf community has been incredibly marginalized by mainstream hearing society in the Philippines, and for generations, the community continues to struggle for equal rights and opportunities in different aspects of life. With the help of sign language, it has contributed in bridging the gap between the deaf community and the hearing majority. And in the Republic Act 11106, Filipino Sign Language, or FSL, was declared as the national sign language, and it mandates FSL to be used in all transactions involving the deaf and should be used in schools, broadcast media, and workplaces. So despite the implementation of RA 11106, majority in the Philippines do not understand FSL, and learning it requires training. As a result, it has led to an undeniable communication gap between the deaf community and the hearing majority. So with the continuous advancement of technology and research, one of the innovation is SLR, or sign language recognition. So it is a collaborative research area which involves pattern matching, computer vision, NLP, and of course linguistics. So it aims to create various methods in order to identify already perceived meanings. So for the past decades of exploration on sign language recognition, in the paper of the research has achieved significant milestones. So in the paper of Martinez and Cabalfin, entitled Sign Language and Computing in a Developing Country, a research roadmap for the next 2 decades in the Philippines, they stated that the Philippines is poised to make an impact on sign language recognition and computational linguistics in the next 20 years. However, fast forward to the year 2022, research on Filipino Sign Language recognition remains limited, and these are the following factors. First is there is no publicly available dataset for FSL. Number 2 is developing FSL recognition system requires expertise in different fields. And lastly, it requires an extensive amount of data and analysis on the linguistics of FSL. And now let's briefly talk about the sign language recognition approaches and the literature that we have reviewed on our paper. So there are actually 3 established approaches in the field of sign language recognition. First is the glove-based approach. So in this approach, it utilizes gloves equipped with sensors like Kinect and other prototypes and use it to gather gesture-related data. And its strength is its accuracy in acquiring gesture-related data. However, its disadvantage is the most proponents are actually expensive. Another approach is through visual-based techniques. So it is widely used in many approaches, and it can capture facial expression, hand gestures, and even body movements. And finally, the hybrid approach, which is the combination of both architecture. Although this one is promising, the problem is that it requires developing a prototype and the challenge of computational setup. And these are the papers that have developed an SLR system for FSL. And so since we don't have a lot of time to summarize the reviewed literature, most of this paper in the FSL recognition research area have applied either visual-based or glove-based approach and has actually achieved good performance in their data. And the paper mostly focused on isolated word recognition, such as Filipino static words, alphabet, and number recognition. On the other hand, our study focused on continuous FSL recognition study using visual-based approach and deep learning. So the main objective of this study is to develop a continuous SLR system for common Filipino phrases using computer vision and deep learning. And the goal as we develop is the SLR is to have these following properties. Robust, meaning that it should be able to recognize the FSL gestures regardless of the background. Second is the integration of non-manual features. Since FSL, like any other sign language, highly relies on facial expression. Third is that it must be time efficient. And lastly, it must be signer independent so that regardless of who the signer is, its age or gender, it still must be able to recognize the Filipino phrase. And now in this section, I will be talking about our methodology in building the continuous SLR system capable of recognizing the sign language of Filipino phrases. So for the data collection, we have undergone 4 processes. First is the formal invitation of signers. And we are able to invite 3 signers. They perform the sign language of 15 phrases in front of the device, and we recorded it using a web camera. So for the table 1, it presents the
You are not audible. Please check your, yeah. Hello.
So each of the phrases is included as they are essential phrases that are commonly used in basic conversations in the Philippines. And here is the documentation of during the data collection process. They are FSL signers. So this is the SLR framework that we have developed. So from the video sequences, it will undergo a feature detection using media pipe heuristic. Afterward, the features detected are extracted using the manual and non-manual features. And after that, it will be processed. It will be pre-processed for the data before the training. Then it can be proceed with the training and the data using the LSTM and ResNet architecture, and the output, which is the corresponding translation of the sign language. So in this process, media pipe heuristic has been utilized to detect the important feature from the video sequences. So just a trivia, media pipe heuristic is an open source technology developed by Google for real-time and simultaneous access to key points of humans, pose, face, and both left and right hand of the user. So because of its capability in providing key points accurately in real time, this technology has been used for detection. It's what we have used using the feature extraction. So one of the deep learning techniques implemented is the long short-term memory, or LSTM. Since it has memory capacity, highly advantageous in continuous SLR models, and it utilizes time series or sequential data, and it is advantageous since there can be a duration gaps in performing different gestures in sign language. Also, LSTM can tackle the vanishing gradient problem usually encountered while using the traditional based neural network. So these are the 5 different setups that we have utilized in the LSTM. Also, we utilize ResNet. So another deep learning is ResNet, or residual network architecture. So it is a type of deep convolutional neural network, and it is a breakthrough architecture in the field of computer vision, achieving not state-of-the-art performances in different classification tests. So we are able to convert this into a one-dimensional ResNet architecture. So with the goal of the SLR model for the recognizing FSL. So table 4, presents the different ResNet model setup. So we actually performed 3 experimental setup. First is the model evaluation, which simply aims to
You are not audible.
Can you hear me?
Yeah.
Okay.
Now it's
This experiment, different facial features, eyes, eyebrows, and mouth has been isolated to see if the performance either improves or declines without the mentioned facial feature. This also aims to rank the importance of each facial feature in recognizing FSL. So last one is the indoor and outdoor experimentation. So this aims to test or investigate the generalization capability of the model, whether the system can also recognize on different signers and in different backgrounds as well. So this is the recorded demo. As you can see, the signer should sit right after the sign right after the disappearance of green text, which indicates start prediction. So the system is capable of recognizing 15 Filipino phrases, which has an accuracy will be discussed in the next part. So it is real time and can predict continuously. And now let's discuss the results of the experimentations. So in the comparative analysis on deep learning architectures implemented, Table 4 presents the different model setups for each technique. It can be seen that the best achieved accuracy is from the LSTM model, which has achieved a 94% on 4 layers of LSTM and plus 3 dense layers. On the other hand, the best achieved model using the ResNet is the ResNet 34 setup. And obviously, as seen in the graph, the LSTM model has outperformed the ResNet 34 model in terms of accuracy, which is significant, and it implies that the LSTM performed better given the FSL dataset. For the feature importance analysis, for its implication, without all the facial features, the average accuracy is only 47.4%, and while complete facial features produce 71.1%. So in terms of ranking the facial feature, the most important is eyebrows, followed by mouth, then eyes. So the analysis shows that the facial features are an important component in predicting FSL. So for this experimentation, for the indoor and outdoor experimentation, the higher...
Presenter, you just have a minute left to conclude.
Just to summarize the experimentation, this is the accuracy achieved for the model evaluation, 94% accuracy. And then the indoor and outdoor experimentation, the result is 72.38% with an average of 0.3 seconds in prediction time. Now let's proceed with the conclusion. Is the SLR system developed is capable of recognizing 15 continuous Filipino phrases. And lastly, we can say that the SLR system is robust, time efficient, and capable of detecting both non-manual and manual features, and it is signer independent. For future direction, we gather more data for a more conversational SLR system, and we also, the goal is to embed the developed model in the mobile application. And that's it. With our study, we hope that we are one step closer to our vision of helping the deaf community have more opportunities in life. That's it. Thank you, everyone.
Yes. Any question from the participants? So, what was the duration of each video?
What?
Video you recorded 360 videos. Isn't it?
We collected 450 videos for this.
Yeah. What was the duration of each video?
What were the? Sorry, I can't understand.
Duration, time. How long it was?
Okay. I think for video it composed of 30 seconds. So if
30 seconds.
Yeah, per video.
Okay. But how did you correlate with that different signs of communication? How many different signs you considered?
15
as far as
sign.
languages
15 sign language.
Yeah.
15 sign language.
Okay. So it's a good application you have developed and good work. Thank you.
Thank you.
Thank you, everyone. Thank you so much. So that is the end of this technical session. I sincerely thank our authors and presenters for their excellent presentation and all our participants for being a part of this international conference. All the presenters would be getting their certificates within 2 working days. I've already dropped a chat, a text in the chat option. I also thank our session chair, Mahesh Bundel sir. Thank you so much for chairing the session, sir. A token of appreciation for you, sir. Thank you so much. So, dear all, I just kindly request to on your cameras for a quick snapshot. If you could on your camera. Okay. Thank you so much. Thank you, everyone. It's great having you all here. Thank you.
Thank you.
Thank you. Bye-bye. Take care.
Thank you.
Bye.